Hi everyone. So this video is going to be a little bit more kind of conceptual than the last couple of videos. It's not going to be so much about being able to calculate or compute anything. It's more going to be about learning to understand a certain type of notation that we're going to be using kind of throughout the course. So just kind of heads up, this will probably feel a little bit different from the other videos. So our goal in this video is going to be able to understand the precise limit definition of the integral. So we'll get into that in a little bit, but just to kind of give you a parallel that maybe you can have in mind, remember that in Calculus 1, so recall that in Calculus 1, you learned the limit definition of the derivative. So how did that work? Well, basically it came from this idea of using secant lines to approximate the slope of a tangent line. And so the limit definition of the derivative says that f prime of x, so the slope of the tangent line at an x value, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And so this expression comes from the idea that, so first of all, this part here is just saying the slope of the secant line between f of x and another close by point. So f of x is like one y value, and then x plus h is just a little bit over from x, right? So you're finding the slope between 2 points that are very close together. And then you're taking the limit because you're trying to take this point and bring it closer to this point. And so if you're bringing h towards 0, that has the effect of bringing the 2 points closer together. So that was the limit definition of the derivative. And if you recall from Calculus 1, you didn't really use that all throughout the quarter, right? You just kind of learned it at the beginning, and it's an important thing to be aware of, but it's not really the way that you actually calculated derivatives. And so similarly, today we're going to learn a limit definition for the integral. And we'll see that it's basically related to this idea, or it comes from this idea of using rectangles to approximate the area. But we're really not going to use that actual limit definition in this class. It's more just something that you should be aware of and you should know how to kind of understand when you look at it. So in this video, oops, changed colors. Let's do this. So in this video, we'll kind of learn an analogous, or maybe I'll just say it this way, an analogous limit definition. I cannot spell today. Limit definition for the definite integral. So the integral from a to b of f of x dx. So in order to understand this limit definition, there's some new notation that we're going to learn. So I have to kind of pause and step away from the idea of basically calculus, where we're not really going to be doing calculus in this next part. We're just going to focus on learning this new symbol and understanding how to use it. So, new notation that we need to learn. Actually, let me say it this way. We're going to learn a new symbol. So first, we need to learn a new symbol. So it's a Greek letter. So the Greek letter, and I guess I should capitalize Greek, the Greek letter sigma, which is written like this. So maybe let me make that a little bigger just so you can really see what it looks like. So that's a Greek letter sigma. It's a capital sigma. It basically represents a sum. So a sum meaning you're adding stuff up. So I guess I don't know for sure, but I'm guessing it's because sigma in Greek is like their letter S, and so S is for sum. So the way that these that we're going to use this symbol, I'm going to write something down that I'm pretty sure is going to look very confusing at first, but I think once we do some examples, you'll feel okay with it. So just bear with me and you'll see this is going to have a lot of different letters and symbols in it. So when we write something like this, so this sum symbol, and then at the bottom, if you write I is equal to, and then I'm writing M, when we actually do the sums, M will be an actual number. So we'll see that this I is going to stay there. M is going to be like I is equal to 1 or I is equal to 2, I is equal to 3, something like that. And we'll do examples in a moment. And then at the top, you have another number. And then next to the sum symbol, you have some kind of an expression. It might have an X in it. It might just be kind of a number, but I'm going to use A with a little subscript of I to represent what it is you're adding up. So again, this I know is like, there's a lot of different letters in this. It probably looks kind of confusing, but once we do some concrete examples, I think it'll become clearer. It's just in order to write down the most general definition, you have to use a bunch of different symbols. So what does this mean? This basically means that you're taking whatever you see here. So this thing here, this is what you're adding up. So you're going to be adding up a bunch of terms, basically. And those terms are going to come from this A sub I. And then what do these other two numbers tell you? Well, this number here tells you the starting point. So it tells you like what is the first number that you're plugging in for I. So you're always kind of taking different numbers and plugging them in for I. And this number M is where you start, and then this number N is your stopping point. So basically this symbol here, you would be adding up, A sub M and then A sub whatever the next number is, M plus 1, and so on and so forth until you get to this number N. So let's look at a concrete example. So let's say that we wanted to take the sum from I is equal to 1 to 5 of I squared. And sorry, let me use the same color here. So what does this mean? This means that you're going to take this A or I squared and you're going to add it up to itself, and you're going to start by plugging in 1 for I, and you're going to stop by plugging in 5. So the first thing we're going to do is 1 squared. And the second thing, and maybe I'll keep using this color, and then the second thing we'll do is we'll add up to that 2 squared. And then to that we'll add 3 squared. And then we'll add 4 squared. And then when do we stop? Well, we see this 5 at the top, and that's what tells us, oh, okay, that's going to be the very last number that we're plugging in for I. So you're basically just, wherever you see the I appearing in this part, that's what you're plugging numbers into. And then you're looking at the bottom and the top to tell you what is the first thing you plug in and what is the last thing you plug in. And so if you add all these numbers up, if I did my math right, I think it adds up to 55. So the way you would read this out loud is you would say the sum from 1 to 5 of I squared is 55. So let's do another example. So let's say that now we wanted to take the sum from I is equal to 2 to 4 of 2I plus 1. So what's this going to look like? Same idea as above. So we're going to be plugging in different numbers for I. The first number we're going to plug in is 2, and the last number we're going to plug in is 4. So the first term in this sum, and I'll keep using parentheses just to kind of separate out the terms. You don't really have to put them, but just to make it clear where each part is coming from. So the first term is 2 times 2 plus 1, because that's the first, that's the first number we're supposed to plug in. The second term would be 2 times 3 plus 1. The third term would be 2 times 4 plus 1. And that's it, right? Because we're only supposed to go from 2 to 4. So when we add these up, we get, so the first one is 5, the second one is 7, the third one is 9, and so together those add up to 21. So that would be the sum from I is equal to 2 to 4 of 2i plus 1 is equal to 21. So basically these two examples, and I gave you an example pretty similar to these on your homework. These two examples are good for kind of understanding the mechanics of how this summation notation works. We won't really be doing stuff like this in this class, but it's really the only way to kind of check, like, do you understand what this symbol means? So the way that we're going to be using the summation symbol in this class is going to be more like this next example. So frequently when we're using this sum symbol, we're not going to be actually adding up numbers, we're going to be adding up algebraic expressions. So another way that you could use this is you could say the sum from I is equal to 0 to 5, let's say. Or actually, let me make things a little bit more open-ended. Let's say to n of x sub I. So when we write down this sum, we're not going to have a number at the end, right? Because we have an x. We're not, like, the x is going to stay there in our answer. So the way that we're using the sum symbol here, it's more like kind of a shorthand so that you don't have to write out all this stuff. Because what would be like the long way to write this? Well, it would be x sub 0 plus x sub 1 plus x sub 2, and then we don't know what n is, so we would have to say plus dot 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 all the way up to x sub n. So this, again, this is like more typical for what we'll see in this class, is that we're not using the sum symbol to actually calculate a number. We're more kind of using it as a shorthand way because, you know, it's a lot shorter to write this than to write all of this, right? So it's just kind of a compact way of writing down the idea that you're adding up a bunch of numbers. Okay, so let's get back to calculus now, and we'll see how we can use this symbol to express the idea of an integral. So why is this sum symbol going to be useful to us? Well, remember that when we're evaluating an integral, if we're approximating it, we're adding up a bunch of different rectangles, right? And so we're going to use this symbol to represent that idea of adding up a bunch of rectangles. And then we're going to use the limit to express the idea that we're not just adding up finitely many rectangles, we want to actually take the limit towards this idea of adding up infinitely many rectangles. So we'll get into all of that in a moment. Okay, so want to just kind of refresh your memory on a few different things that we talked about in the last couple of videos. So first thing is that if you're taking the integral from a to b of f of x dx, so remember that means the area bounded by the function and the x-axis between x is equal to a and x is equal to b. And so one thing we talked about in yesterday's video is that that area could be positive or negative. It depends on whether it lies above or below the x-axis. So you're kind of adding together all these areas, and they're allowed to kind of cancel each other out if some is positive and some is negative. So we'll see actually like next week how we can exactly calculate these areas, but for now we were just approximating them. And the way we were approximating them was we had kind of three different types of sums. So one was taking all of these rectangles where you're using right endpoints and adding them up. Another one was doing the same thing but using left endpoints. And another one was doing the same thing but now using the midpoint of each interval. And we'll get into this idea in a second, but basically we've seen that the bigger this number n, the better your approximation is. So if you're only using a couple of rectangles, you know, this symbol is probably very rough, right? It's not going to give you a good approximation. We've seen that in yesterday's video and the worksheet that went with it as well. But the more rectangles you use, the better, basically. So how can you find the exact value? Or maybe I shouldn't say how can you find, but what is the exact value the exact value of the integral from a to b of f of x dx is going to be the limit as n approaches infinity of Rn, which is the same thing as the limit as n approaches infinity of Ln, which is the same thing as the limit as n approaches infinity of Mn. So why are we taking the limit? Well, it's just to express this idea that basically the more rectangles, the better. And if you really push that idea of more rectangles to its limit and imagine that there's infinitely many rectangles, that will give you the exact area. So it's not really possible, right, to have infinitely many rectangles. Infinity is not a number. And so that's why we have to use the concept of a limit. So limit is all about kind of pushing in that direction and kind of seeing where the values are approaching. So I just want to kind of show you again on Desmos what is going on with these rectangles, to also kind of remind you why it doesn't matter whether you're using right, left, or middle. So this is just some random function. And I just want to show you first. So this right now only has 6 rectangles, and you can see how it's like very chunky and it doesn't really fit the curve that well. And so right now it's set up for a right-hand sum. If I move it to a midpoint sum, it looks like totally different, right? Those look really, really different. And then left-hand sum, again, different. Like these are all going to give you pretty different numbers. But now so I'm just going to bring it back to the right endpoint. So if I now increase the number of rectangles, we can see that the approximation is getting a lot better, right? The rectangles are really kind of fitting this curve really well. And now if I switch it, so right now it's on right-hand sum. If I now switch it to the middle, it like pretty much looks the same, right? Like you can see it shifting a little, but it's really not going to be that different. And then this would be left-hand sum. So the difference is just really not going to be, it's like shifting, but it's kind of like the same area, right? Whereas when we had fewer rectangles, there was a difference. And so that's why when you're taking the limit, it doesn't matter whether you're using right, left, or midpoint sums. Okay, so the next thing we're going to do is we're going to figure out a way to express this idea. So we're going to express this using sigma notation. Okay, so I'm just going to draw kind of a sample graph. So let's say that we just have some function, and I'm just going to make it lie above the x-axis, but it doesn't really matter whether it does or not. So let's say we have some function that looks like this. So this is f of x. And let's say we're trying to take the integral from, let's just count a as being at 0, and then let's say b is over here. So how can we approximate this area? Well, we saw that we can use rectangles, right? So I'm just going to draw in, I'm not going to be very exact here. I'm just going to draw in some kind of sample rectangles because I'm not going to be exact about how many. I'm just going to kind of draw a few and then do like a dot, dot, dot. So we'd have like one rectangle here, maybe another one here, another one here. I'll do one more. And then we have like dot, 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 and then I'll do one over here. And the reason I'm being vague and doing this dot, dot, dot business is because we're going to be taking a limit, and I don't want you to be focused on exactly how many rectangles are here. The idea, let's just imagine that we have n rectangles, right? We have any number of rectangles in this picture. So looking at this picture, the width of each of these rectangles, we can call that delta x. Okay, so delta x is the width, or maybe let me say it as base, because that's the word that we often use when we're taking the area of a rectangle. So the base of each rectangle. And so why are we using the symbol delta? So if you've probably seen that symbol come up in your Calc 1 class, and it comes up a lot in science classes. So the delta symbol means change. So delta x, and usually it's meant to represent like a small change. And so delta x just represents, a small change in x. And so when you're, doing this kind of a process, you're going to get a better approximation the smaller the rectangles are, the more narrow they are, right? And so that's why we use this delta, because usually we're representing like a small change in x to give you a narrow rectangle so that you have a lot of them. Okay, other thing I want to put into this picture is that, so here, the way I drew it as a right-hand sum. We'll see that that doesn't really matter, but I'm just going to kind of continue with that idea. And I'm going to call the right endpoint of the first rectangle x1, the right endpoint of the second rectangle x2, the right endpoint of the second or the third one x3, x4, and so on. And, by the time we get to the end, it's going to be xn. That's the nth rectangle. Okay, so now that we have all of this kind of general stuff written down, let's try to write down what the area of a rectangle is going to look like. So the area of each rectangle is, and I'm going to write this actually usually we say base times height, but I'm going to write height times base just because it will fit better with the kind of format we want these to be in. So how would you find the height of one of these rectangles? So I'm actually going to do something. I'm going to just kind of put a random rectangle in here. And let's think of this as being the ith rectangle. So I'm going to call this endpoint here xi. So usually when you say something like xi, you mean like, I don't want to be specific about which one I'm talking about. I'm just going to say some rectangle. So xi is the ith rectangle. So how would we find the area of that rectangle? Well, we know that the base is delta x, right? So I'll put that in as our base. And then how would you find the height? Well, if our function is f of x, you would be plugging in that right endpoint. So you would do f of xi. So f of xi represents the height and delta x represents the base. So that's how you would find the area of one rectangle. But when we're doing this, we want to actually add up a bunch of rectangles. So the sum of all the rectangles or I should say the sum, I'm not going to write it, but the sum of the area of all the rectangles is going to be basically the same expression that we wrote above, but for all the different numbers. So we would have f of x1 times delta x plus f of x2 times delta x and then going all the way up to, we don't know exactly how many rectangles, so we're just going to use xn. So f of xn times delta x. Okay, so how can we write that as a sum, or using sigma notation? Well, it would look like this. So we would want to say that it's the sum from I is equal to 1 to n of f of xi times delta x. Right? Because that's what that sum symbol means, that the symbol just means that you're adding up a bunch of things and you're plugging in different numbers for I. So we would get x1, x2, x3, all the way up until this number n. So right now, what we have written down is basically just a way of writing down a Riemann sum, right? We're saying we're adding up n rectangles. So maybe I'll even, it says it above here, so actually I won't write it again, but this, you just want to think of this as representing the sum of the areas of n rectangles. However, we don't want just n rectangles, right? We want to take the limit. We want to get the actual area. So to find the actual or the exact value of the integral from a to b of f of x dx, we want to basically bring the number of rectangles towards infinity. And I'm actually even going to say to infinity. And again, I just want to be clear, infinity is not a number, but that's why we're using limits. It's this idea of kind of approaching infinity. So how can we take the expression that we just had? Well, we can now just throw in a limit. So I'm going to actually use one new color just because it will help to demonstrate something in a moment. But so if we take the limit as n approaches infinity of the sum from I is equal to 1 to n of f of xi times delta x. So I know this looks like a lot. This is a lot going on. But all this means, so if you understood this step, right? This step up here, what was this about? This was just saying we're adding up the areas of a bunch of rectangles. That's really all I want you to kind of see that as. And then what are we doing here? We're just taking that, adding up all of those rectangles, and we're increasing the number of rectangles. That's what this part represents. We're taking, we're making it be the sum from I is equal to 1 to 100. That would be 100 rectangles. Then we're increasing that to 1,000 rectangles. Then we're increasing that to 1,000,000 rectangles, and we're kind of seeing where that's going. So if you take the limit, that's where you're going to get the actual value of the integral. So this expression written down right here is going to be equal to the integral from a to b of f of x dx. So the reason that I'm using this color coding is basically to kind of show you where the different components of this integral symbol come from. And especially I just want to emphasize that I want to emphasize kind of the dx and where that comes from. So basically think of the limit and the sum together, those turn into an integral symbol. So you want to think of the integral symbol as meaning that you're adding up infinitely many rectangles. So that is kind of combining the idea of the sum and then the limit together means you're adding up infinitely many rectangles. And then what does the f of x represent? Think of that as representing the heights of all those infinite rectangles. And then what does dx represent? You can think of that as representing the width of each of those rectangles. And when you use d instead of delta, that actually means kind of even smaller. So delta x means like a small change in x. dx means an infinitesimal change in x. So a change that's so small that you couldn't even really detect it. And so if you're adding up infinitely many rectangles, they're going to be very, 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 very thin. So this is the official kind of limit definition of the integral. So the last thing we're going to do in this video is a few examples where we're going to practice going from the limit definition to the integral form. So we're going to look at a few specific examples of limits and figure out how to rewrite them as an integral. So for example, this first one, we're going to express the following limit as an integral on the interval from 0 to pi. And so it's the limit as n approaches infinity of the sum from 1 to n of xi cubed plus xi times sine of 5xi delta x. So that's a lot, right? It looks very complicated, but fortunately, this style of question is actually not very difficult to answer because all we really have to do is go back to that limit definition and figure out which parts of this limit translate to what different parts of the integral. So we saw in our limit definition that together the limit and the sum, those together become the integral symbol, right? That's really what an integral symbol means. It means an infinite sum, a sum of infinitely many tiny rectangles. And then additionally, notice that there's no a or b in this left-hand side, right? The limit and the sum don't have an a or a b in it. And that's because they're kind of a little bit more general. And so you do need to be told what those a and b are if you're given your limit in this form. And so if we go back to our example, we can see that we're told that we're looking at the interval from 0 to pi, and so that is going to be our a and our b. So what that means is that this part here is going to become the integral from 0 to pi. Okay, so next up we have this whole kind of complicated looking part. So looking at our limit definition, what part is that? Well, that has to be f of xi, right? So that means that we have some function f of x that has been evaluated at xi. So what that tells us is that if we're trying to figure out what is the function in our integral, then all we have to do is take the function that we see in the limit, and instead of writing xi, just write x. So all of this stuff here, it basically tells us directly what our function is. Our function is going to be x cubed plus x times sine of 5x. And that's it. And then the last part, as we talked about, is how this delta x, that was like the width of the rectangle, that becomes dx to represent the fact that now we have these very, very tiny, infinitesimally thin rectangles that we're adding up. So that's it. Kind of a complicated looking question, but really not that difficult to answer. It's just kind of being able to identify the different parts of the limit and translate them into the integral. Okay, so let's do another example. So this one's going to be pretty similar, and then we'll do one more that has a little bit more going on. So I would encourage you, if you didn't for the last example, to pause the video and try this one yourself now that we've done one of them together. Okay, so again, just like with the last one, we know that the limit and the sum together, those become an integral symbol. And then the bounds are given to us, right? We're told that we're looking at the interval from 0 to 1. And so those are going to be our bounds. And then next we have this part, which is the function evaluated at xi. So we just need to take this function and rewrite it with x instead of xi. And so we have e to the x over 1 plus x. So not as complicated a function as our last example. And then last part, as we saw, is that this delta x becomes dx. So that's it. I know this might seem a little silly, like what's the point in kind of going back and forth in between these, but what we'll see later in the class is that there's going to be a variety of different topics that we're going to, in understanding where certain formulas come from, we're going to start by building them up using this limit definition. And it's going to be important in order for you to understand the formula for you to be able to go from the limit definition to the integral form. Okay, one last example. So this one's going to start off like the last two. We're going to take a limit and we're going to rewrite it as an integral, but then we're actually going to evaluate the integral. So this is just kind of a throwback to earlier when we learned how to evaluate certain types of integrals. So we haven't learned how to evaluate, for example, this integral, right? And we haven't learned how to evaluate this integral. But we have learned how to evaluate certain types of integrals if we can use area formulas. So we'll see that we can do that in this case. Okay, so just like with the last few, we're combining this limit and sum to give us our integral symbol. And we're given that we're looking at the interval from 1 to 4. So those are our bounds. And then this next part here, well, this is f of xi. And so we can rewrite this as f of x by just replacing x with xi. So we have negative 2x plus 6. And then finally, we have delta x, and that becomes dx. Okay, so how do we go about evaluating this using what we've learned so far in this class? Well, this is the area, right, bounded by the function f of x is equal to negative 2x plus 6. And so what we want to do is we want to graph the function f of x is equal to negative 2x plus 6, and then look at what is the area between that function and the x-axis from 1 to 4. So we did a lot of examples like this earlier on. Okay, so let's start by graphing negative 2x plus 6. So that's going to be a linear function, right, with a y-intercept of 6. So something like this. So that is our function. And then we're supposed to be going from 1 to 4, right? And so I'm going to just kind of mark off where our 1 and our 4 are. So there's 1 and there's 4. And then we're looking at the area between the function, and let me maybe just label this, and the x-axis. And remember, as we saw in earlier videos, that we're counting the area that is above the x-axis as positive, and then the area that is below the x-axis as negative. So we just need to figure out what each of these areas is. So for the first area, we have a triangle where the base is 2 and the height is 4, right? So we have 2 times 4 divided by 2. And so that is going to contribute positive area, but then this red rectangle is going to contribute negative area. So this is going to be minus, and in this case, our base is 1 and our height is 2. So we have 1 times 2 over 2. And so altogether, this is going to give us, so for the first one, we have 2 times 4 over 2, so that's just going to be 4. Maybe I'll keep going with my color coding. And then we'll have minus 1 times 2 over 2, so that's just 1. And so we end up with a final answer of 3. All right, so that is it for this video. As always, please check out the worksheets the worksheet and the homework questions that correspond with this video to get some practice, and I'll see you all in the next video.